In this video, we'll take a brief look at the life and contributions of Galileo to astronomy and physics. A few biographical notes here. Galileo Galilei, in his time it wasn't unusual for the oldest son to be given a name that was based on the family name, and so that's why they're so closely related there. He's pretty much known by his first name, Galileo, but sometimes you'll hear both. 1564 to 1642, so he was born 21 years after Copernicus died. He happened to die the year that Isaac Newton was born. He was the son of a well-known lute player and a music theorist, and I just discovered reading this morning that his father actually made a discovery of the relation between the tension and a string and the speed at which waves move along the string. His father made a contribution to science as well. He was never married, but he had 3 children with his mistress, 2 daughters and a son. His 2 daughters went into a convent, and Galileo was the primary financial support for that convent for many years. He was one of the first experimental scientists. Stephen Hawking and Albert Einstein have credited Galileo with being the first modern scientist. He made a lot of contributions to astronomy and physics. I'm going to talk about some of his contributions to physics first. Among them, studies of pendulums. He discovered that the period of a pendulum is independent of the size of the swing. It depends on the length of the pendulum, but not the side-to-side motion. Now, it turns out this was later corrected. Galileo didn't have the mathematical tools to determine that there is some dependence on the size of the swing. In his day, it would have been impossible to measure the time difference. There were not good clocks in those times. In fact, one of the things Galileo used as a clock was to imagine the beat of a rapid piece of music and maybe imagine 16th notes in that piece of music and use that to determine how long a time period was. He studied projectiles, and he realized that in the absence of air resistance, the path of a projectile will be a parabola, a particular mathematical shape. He also realized that this couldn't be extended to very large motions, but that for small motions, like those of the best cannons of the day, they would be parabolic. The path of the projectile would be. Speeds of falling objects. He realized or discovered that in the absence of air resistance, a feather and a hammer would fall at the same speed, and there happens to be a nice video of that.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, that was from the Apollo 17 moon mission, seeing the feather and the hammer falling at the same speed. He came up with something that's considered the basic principle of relativity, and his idea was that if you were in the hold of a ship and that ship was at rest, or if it was moving through calm water at a constant velocity, you wouldn't be able to do any experiments that would determine the difference between the 2 situations. And the way it's often expressed is that the laws of physics are the same in any system moving at a constant speed and direction. Isaac Newton used this in studying motion, and a little bit later, Albert Einstein used that Galilean principle of relativity when he first developed the special theory of relativity. The first law of motion, which we credit Newton with, but Galileo had a form of this. He had the idea that objects would retain their velocity without impediments to their motion. And so if there wasn't any force slowing them down, they would continue to move in a straight line with constant speed. He also discovered experimentally that the distance traveled by an object when it is undergoing uniform or constant acceleration is proportional to the square of the time that has passed. So lots of contributions, and he did many of these things by experiment. And so in that sense, he was a modern scientist. That's what people do nowadays. Before that, it was more about talk than about experiment. More contributions. Now we'll start to concentrate on his astronomical contributions. He made improvements to the telescope. In 1609, he heard of an instrument that had been built by someone up in the France-Belgium region, a Flemish optician named Hans Lippershey. Just from a verbal description of this, Galileo was able to build his own simple telescope. The first one he built was a 3-power telescope, which isn't particularly good, but eventually he was able to build about a 30-power telescope. He didn't wait too long before turning the telescope to the night sky and starting to study things in there. He made publications about astronomy and science in some language other than Latin. In those days, almost everything scholarly was written in Latin, but Galileo would put things out in Italian. Some of his observations were imperfections in the heavens. When he looked at the moon through the telescope, he could see craters and mountains. And if he did eyepiece projection with the telescope, you don't want to aim a telescope at the sun, you'll fry your retinas. But if you take that telescope and project its image onto a piece of paper, that's called eyepiece projection, he could see sunspots on there. Imperfections in heavenly objects. People didn't believe such a thing was possible, but he saw them. Observations of Jupiter's moons, which the 4 moons that he could see through his telescope and that you can see through an inexpensive pair of binoculars, are now called its Galilean moons. He determined that they orbited Jupiter with regular periods. Now, why is that important astronomy-wise? One of the arguments against the Copernican model was that if the Earth was orbiting the sun and moving through space, it would leave the moon behind. But the moon somehow stayed with the Earth. Well, Galileo looked out at Jupiter and saw that it had moons that moved through space with it. So if Jupiter did, why couldn't the moon stay with the Earth? He didn't have a theory of gravitation. In fact, he didn't think such a thing existed. But other scientists soon, Kepler started proposing that perhaps there was a force that Jupiter exerted on its moons and the Earth exerted on its moon. So that eventually led to Newton developing the law of gravitation. Interesting thing about Jupiter's moons, Galileo proposed that because of their regular periods, they could be used as a sort of universal clock. And one of the difficulties that people had in determining their longitude while at sea was having a decent clock to use. And Galileo proposed using Jupiter's moons as clocks. In the early 1800s, when Lewis and Clark were planning their expedition out to the west, Meriwether Lewis was taught by a particular person how to use Jupiter's moons as a clock and determine longitude that way. And the person teaching Meriwether Lewis how to do this was President Thomas Jefferson. I don't know if any president since would have had the ability to do this, but Jefferson did anyway. Galileo saw a full set of phases for Venus. Why is that important? Because in the Ptolemaic model, you should only be able to see crescents. In the Copernican model, you should be able to see the full set. Galileo did see the full set. This is just kind of a cartoon drawing of how you could see the full set of phases for Venus. Here are some photographs that were taken in 2004 showing more or less that full set of phases for Venus. Notice when Venus is farthest away from the Earth and appears smallest, that's when you can see the biggest phase. This would be a gibbous Venus in this picture. And then as it comes closer to us is when we see the crescent phases. I have another one of the animations that we can see these with. This is the Copernican planetary phases. In the earlier video you would have seen the Ptolemaic planetary phases. In this one you can see those predicted by the Copernican model. There you can see as Venus gets far away, we start to see a full Venus. It's hard to see Venus when it's right near the sun, but if you could, it would. But you can see definitely a gibbous Venus at times. We've seen the retrograde motion simulation before. Galileo was very much a strong supporter of the Copernican model, right down to the epicycles that Copernicus had built into it. It got him into a little bit of hot water at one point. He was on the wrong side politically in an argument and offended the Pope. However, Galileo basically started modern science and made significant discoveries that supported the sun-centered model.